Okay, so it's about 6:05, so I'm gonna get started. So welcome everybody who has decided to join. This is going to be the time series forecasting workshop for the UW Data Science Club. I'm happy to see you guys all here. Just to introduce myself, my name is Matthew Erxleben. I'm actually on my third co-op right now. I'm in Toronto, but I'm going into 3A of management engineering in January. So yeah, I'm super excited to get started here. I'm an exec on the data science team for the education group, and it's been a blast so far. So really excited to do this workshop for you guys. Okay, and so the first thing I want to mention, for anybody who's here, any newcomers, I do really recommend you guys check out the new member sign up link. It's on the screen here. If you can just put that into your browser and sign up for the Data Science Club. I really recommend it. It's a great opportunity to learn more about data science as well as meet people in the field with similar interests. I really recommend it. The Data Science Club is really an awesome place to learn as well as to have some fun. So yeah, really recommend that. Okay, so getting into the workshop. So for everybody who is unaware, this workshop is going to be about time series forecasting. The idea of this workshop is to give a general overview of a lot of the different things in time series forecasting and time series analysis in general. A lot of it can be a little bit daunting when you look at it in terms of like all the different terms and all the models and the coding. And so the idea of this workshop is to be very beginner and just give you guys an overview and a lot of different terms in time series forecasting so you understand. And we'll also be getting to a point at the end of the workshop where I'll be showing you guys in code the ARIMA model, right? So that's going to be what we're working up to. And throughout the workshop, we're actually going to be doing a lot of different things discussing time series forecasting. So the first thing we're going to talk about is what is time series forecasting, or what is time series data as well. So, excuse me, a lot of time series problems, they need to be defined. And so just to understand what that actually is very, very important, and what forecasting is. We're also going to talk about common time series forecasting models. We're going to be looking at what seasonality is, what stationarity is, and what differencing is, what autocorrelation is, what autoregression is, what a moving average is, what an ACF and PACF test are. And then finally, we're going to be looking at the ARIMA model in code in a Jupyter notebook. And so some prerequisite knowledge I would say I recommend for you guys to have before this workshop. I'm going to say it's a very, very beginner, so I wouldn't worry about this too much. But I would say having a general idea of what Python is and how it works is important to understand the code chunks as a part of this workshop. Just so you know, like on a basic level of how Python runs as like a programming language. Some basic statistics. I would say that if you guys have done stats in high school or maybe a first year class in stats, you should be completely fine. Nothing really, we're not diving into theory really in stats. Just a good idea to have some basic stats knowledge to understand some of the concepts we'll be discussing regarding time series analysis. Beginner level data libraries. So libraries like pandas, matplotlib, and numpy. And we'll also be using stats models in this, but just having an idea of what those libraries are. In terms of like pandas, for example, it's just a very basic data manipulation library you can add to Python, where you can bring in data and manipulate it in data frames. We actually had a workshop on pandas a couple of weeks ago, so I recommend you guys keeping a lookout at our YouTube channel for that to be uploaded. As well as like matplotlib, which we're using a little bit just to show us some of the graphs, just to have an idea of how those work. And then as well as experience with Jupyter notebooks. I say that because the screenshots that I'll be using in this workshop are going to be from Jupyter notebooks. If you guys aren't familiar, Jupyter notebooks is just a code editor that you can use online in your browser. And it allows you to have little bits of text as well as code chunks in between. So it looks really nice. It's really good very popular in data science. It's very good for like showing data visualizations and that sort of thing. So I recommend having some of that prerequisite knowledge so you're not too overwhelmed when coming into the workshop here. But I promise it's pretty beginner, and we'll walk through it pretty simply. So the first thing I want to talk about is what is time series data, right? So time series data is historical data that has a singular value per unit of time. And so as you can see on this little graph here on the right, you can see on the x-axis you have dates over time, right? And so you have from 2021 to 2022 all across the x-axis, and on the y-axis you have some sort of value, right? So this is sales by some sort of sales for each date. And so as you can see, you only have one y value per x value, and that's over time. And so that's how time series, univariate time series data actually works. And examples of this would be like, let's say you're at a grocery store and the grocery store is selling bananas, right? As most grocery stores do. And let's say that they're selling these bananas and they're tracking their weekly sales of the bananas over the course of the year. So let's say this graph on the bottom right, that's showing how many sales weekly they have of bananas each week. And so that's an example of what time series data actually is. There's only one number of banana sales at the store on each given week. That makes sense, right? And so some common time series data sets, it's a very, very common form of data, would be like sales, like we talked about with the bananas, or stock prices, or daily temperatures, or somebody's weight over time, or anything like that that's over time with data. And so, yeah, it's very, very common. Hopefully that explains that. And so the next thing I want to talk about is what can we actually do with time series data. And so data might have some sort of trends or relationship to another. And this can be autocorrelation, seasonality, external factors that are a trend across data. And so based on the data's relationships, we can actually forecast into the future to predict what a value will be in X amount of time. So for example, let's say we can actually predict how many bananas the grocery store is going to sell next week. So let's say we know that, okay, the grocery store sold 500 bananas 2 weeks ago, and last week they sold 200 bananas. Well, how many bananas are they going to sell next week? We can use its previous data in time series to actually predict what that's going to be, what that value is going to be. And that's all based on its relationships and trends in the data. So I wanted to point this out. Like I said, we will be showing off some code chunks from a Jupyter notebook. Here's just me importing some libraries that will be necessary for some of the coding in this workshop. So here I just imported some libraries as well as some models from stats models. And also we loaded in some sample data from Kaggle, just some very, very basic sales data. And so it's a historical data set from 1991 to 2008. All you have is just a date and the other in one column, and in the other column is just the value. And so here's an example. Here's showing off just a matplotlib chart of time series data. It's very, very simple. As you can see, over time, the value is increasing. That's some sort of trend we can see. And yeah, there's only one value in the y-axis per value in the x-axis over time, let's say, right? Okay, so some commonly used time series forecasting models. So there's a couple of commonly used time series forecasting models, and we'll be discussing some of them. A lot of them build up into what's called an ARIMA model. But the first one is called an AR model, so an autoregression. The next one is called a moving average. Oh, it's an MA model. The one after that would be an ARMA model, which is an autoregressive moving average. And then the one after that would be an ARIMA model, which is an autoregressive integrated moving average. So it seems like a lot of words, but trust me, we'll walk through it. We're going to be discussing what an AR model is, what an MA model is, and then combining all of that into an ARIMA model at the very end. So, like I said, with time series data, there can be a lot of trends and relationships with its past data you can use to actually predict what's going to happen in the future. And so what are some of these trends? Well, the first one I want to discuss is called seasonality. And so seasonality is a trend that occurs in time series data, and it's a predictable trend or change that reoccurs every single calendar year at the same time due to the season or some time of the year or at some point in time. So an example of this can be like Black Friday sales. Let's say your store is tracking their sales, and in November, their sales skyrocket because every November there is a Black Friday. Or let's say another retail store is tracking their sales and they're also looking at December. Let's say December sales skyrocket because of Christmas shopping. And that occurs every single year because it's due to the season, right? It's due to the seasonality of the data, if that makes sense. And so here's a graph on the bottom just displaying what seasonality actually looks like. As you can see, there's a spike and there's a drop at the same time every single year in the time series. Okay, so the next thing I want to talk about is stationarity. So that's discussed a lot with time series. And so stationarity is really important if we want to be able to forecast or actually predict what's going to happen in the future. It's required for a lot of models to actually work because it makes it so you're almost taking out a lot of those trends, and instead you're just looking at a time series that's stationary. So what does stationary actually mean? Well, the first thing is that, like I discussed before, seasonality. Well, you actually don't want to have seasonality in order for your time series to be stationary. And this is because you want it to be as simple as possible, so you have a clear relationship between the X and the Y variable, which is the time and the whatever value you have. The other thing that stationarity requires is to have a constant mean. And so as you can see with these graphs on the right side of the screen here, you can see that there's one graph that shows mean, which is constant with time, and there's one graph that's showing mean that's not constant with time. As you can see, the mean is also it's going off of its center line, right? The data is going upwards over time, and it's not what you want if you want it to be stationary. And then the other thing is having a constant standard deviation or variance, and so that would be the distance between the average across a time series. So as you can see in the graph as well on the right side, the distance down is a lot further from the middle of the time series than the top. And so the variance is changing with time, and we don't want that. That's not being stationary. However, you're going to encounter a lot of non-stationary data when you go through and look at any data set, any time series data set. So if we need our time series to be stationary to do forecasting, how do we actually make it stationary? Well, I have the answer. So the answer is to do differencing. And so this is one of the answers that you're able to make a time series stationary. And this is actually by taking the difference between consecutive values in a series. So if you think about it, like if you have a line, right? And so you know that a line has a rise and a run, right? If you are to do like a y2 minus y1 over x2 minus x1, you're able to find the slope of the line, right? And so that's basically what differencing is that you are taking the difference between two data points to find the linear increase, or differencing. And so an example of this would be like the banana sales last week was 10, and the banana sales in the current week is 15. So the difference would be 15 minus 10, and that would be 5. So now your new data point for a difference time series would be 5 for the current week rather than 15. If that makes sense, right? And so this is used to make time series stationary. And you can actually use multiple orders of differencing to be able to get closer and closer to stationary. Because believe it or not, doing this just once, sometimes for some time series, isn't enough to make it close enough to stationary. Another thing to notice with being stationary and differencing is that you can over difference. And so you don't want to do too many orders of differencing to where your data is not usable anymore. You want to be just before it's over difference. So it still may not be completely stationary, but it's still important to keep that in mind when you are differencing your time series. We do have some chat. Are we allowed to ask questions during the session or at the end? I do have a slide at the very end, just saying any questions. But if you have any questions right now, you can put them in the chat and I can discuss them as we go through as well. No problem. I will continue though. So if you have any questions, to put them in the chat and I'll get to them when I see them pop up. So on the screen here is actually an example of differencing. Oh, okay, cool. An example of differencing. And so as you can see here, this is also from the Jupyter Notebook. We have a code block here that's just using so it uses the .diff function. And so it's just plotting the value from the data frame using the .diff. And as you can see now, the time series looks a lot different, right? So as we know, this is what the time series used to look like, right? So it used to be this, as you can see, this increase over time, definitely not stationary, right? As we know, there's not a constant mean. The mean's changing over time. There's not a constant variance, and there's seasonality. As we can see here, it's much more centered around the mean, right? It's much more of a constant mean. There's still a changing variance over time. There's still a bit of seasonality. With a second order of differencing, we can see that it's much more closer to stationary. We basically have a constant mean and we have a constant variance. There is a bit of seasonality, but we don't want to over difference. So we are pretty close to being stationary from this graph, as we can see on the right side. And so what this means is that we use a second order of differencing to make the time series stationary. Okay, so another thing I wanted to discuss, and actually just to say, any questions on differencing or stationary or seasonality or anything like that, you guys can put them in the chat now, or I can just move on if it sounds all good to you guys. Sounds good? Okay, I guess we will move on. So the next thing I want to talk about is autocorrelation. So once again, I talked about different trends with data, right? And with a time series. So autocorrelation is another trend that can happen, which it basically means that the data has a relationship with its own historical data. Now that can sound confusing, I know, but we'll walk through this. So let's just think about the banana sales, for example. So as an example, let's say that the amount of bananas that were sold last week actually has an effect on the current week's banana sales. So let's say that the grocery store sold 500 bananas last week. And this week, let's say maybe they're all sold out of bananas. So that's going to make it so there's probably going to have a lot less sales this week due to all the bananas being sold out. So that is actually an example of what autocorrelation is. It's showing a correlation between a previous data point, how it's affecting a current data point, or the next data point, the ones in the future. So that can actually help us predict, oh, hey, how is this going to affect our forecast or our predictions, right? Hopefully that makes sense to you guys. So an extension of what autocorrelation is what an autoregressive model is. So remember in the beginning, I talked about the different models that are involved in time series forecasting and analysis. An AR model is a very simple one that is used a lot. And what it actually means is that all it's doing is it's using previous data points from a time series to forecast future data because there's an autocorrelation like we talked about. So you would have, like, let's say, oh, well, I want to know how many bananas the grocery store is going to sell next week. Well, one of my values in my model is going to be the previous week's banana sales. And that's going to keep going as we go through time. And so now you have a bit of a prediction to where, depending on how many bananas you sold in the previous week, that actually affects how many you might sell in the next week. And so that's what an AR model is. And so it uses the parameter P, which represents how many terms you're going to use, or how many previous weeks, let's say, you're going to use in your model. And so that's actually what's called a lag. So I know that can be a strange word, but all a lag actually is how many previous data points you're going to use. So let's say you want to use just the previous week of in an AR model. Then that would be a lag, you'd be using one lag, and your P would equal 1. And so it represents how many lag terms are actually used. And so let's say you want to use the previous 2 weeks of your banana sales data. Then you're going to use 2 lags, and your P is going to actually equal 2, which is P is the parameter, right? That's used in the AR model. And this is going to make sense once we get to the ARIMA model at the end. But like we said here, like I just explained, we see a correlation between previous week's banana sales and the current week's banana sales. Therefore, we use the previous week's banana sales to forecast future banana sales. That makes sense, right? So if you use the previous 2 weeks, then it would P equal to 2. Previous 3 weeks, P would equal to 3, and we're using 3 lags. Let's see, any questions? Is autocorrelation similar to an eigenvector problem? That's some linear algebra, and honestly, I'm not caught up on my linear algebra to be able to answer that question. Alvin, if you want to talk about the eigenvector problem, I'm not really sure. Sorry. How does one decide the lag value? Okay, that's a very, very good question. So that's actually exactly what we're getting into next. So what should P actually equal? It's like pretty common follow-up question that you'll have when you're looking at AR model. So a way to actually know how many lags to use in an AR model is using a partial autocorrelation function. So that can sound confusing, but it's actually very simple. And what it means is that it's just the direct correlation between a lag and its series. So let's say you have the previous 3 weeks of banana sales, and you have the next week's banana sales you want to predict, right? All a partial autocorrelation function is doing is it's telling you the significance or the correlation between that 3rd week and how it directly affects the next week, the week you want to predict. And also it will tell you, okay, the 2nd week, how does that directly affect the week you want to predict? And the last week, how does that directly affect the week you want to predict? And so it's a function that we can use, and we'll see a graph of this in the next slide. It's a function you can use to see how many lags are actually significant in an AR model, because you don't want to use too many lags or else it's not necessary, right? So P is equal to the number of significant lags found in the PACF test. And so here's an example of PACF in the Jupyter notebook, like I described. And so as you can see, we can use PACF to see how many AR terms to actually use, or the number of lags to use. And so here I'm plotting the PACF, and this is also, by the way, from stats models. I imported PACF, and so I'm plotting it using the value. And so we can see right here the first lag is very, very high. So on the x-axis, this is the number of lags, and then on the y-axis, this is the level of significance, right? So as you can see, the first lag here is really, really high up, and it's very, very outside of the bound. So it's very, very significant. And so the ones after that, this is not that far out of the level of significance. You could use a 2nd lag, but these ones, they get to be pretty close into the bounds, and they're pretty insignificant. And we get to this one over here, which is about an 11th lag, and it seems to be outside of the bounds of, and is very significant, but because it's such a lag that's so far back that we don't want to overcomplicate our model. So for right now, it seems like the best approach would just be to using a P equal to 1 or 1 lag in our model for an AR model, right? Let's see. Okay, so I will be continuing to a moving average. So moving average is similar to an AR model. It's almost, you can kind of think of like the opposite. It's very similar. You're going to notice a lot of similar parts about it. So an MA model or moving average model uses previous lags errors to actually forecast future data. And so what does this mean? So think of it like an example of a model that predicts banana sales based on the error of banana sales in the previous week. So how many was it actually off in the forecast? And so Q is going to be the parameter to represent how many lag forecast error terms to actually use, which is similar to how we used P in the previous one with an AR model. And there can be the error from a previous week or previous 2 weeks, and that would change the value of Q for an MA model. And so, like we said before, what should Q equal to? Well, Q should equal, we can figure that out what Q should equal by using the ACF, so the autocorrelation function. So very similar to the PACF, but instead we're using an autocorrelation function, so not a partial, just an autocorrelation function. And this is actually the non-direct correlation between a lag and its series. And so if you remember, I talked about how you have, let's say you had 3 lags and you're projecting how many banana sales you're going to have. You have 3 previous weeks of banana sales, and you want to look at those. And in a partial autocorrelation function, like we use in the AR model, it was the direct effect of those weeks on the current week's data. With an ACF test and with an MA model, we actually aren't looking at the direct effect. We're looking at the non-direct correlation between the lags and series. So as you know, if you were to have 3 weeks of lag, well, the data from 3 weeks ago is going to have an effect on the data from 2 weeks ago. And the data from 2 weeks ago is going to have the effect on the data from 1 week ago. And the data from 3 weeks ago is going to have an effect on the data from 1 week ago as well. So there's a lot of indirect correlations between the data. And so that's what an ACF test does. It tells you which lag to use, and it does it through telling you which lags are significant in terms of its non-direct correlation between a lag and its series. And so Q is going to be the number of significant lags found in the PACF test. So it's very, very similar to the PACF test. Sorry, I think it's a PACF. I mean ACF test. It's very, very similar to the PACF, but it's a little different. So as you can see here, it looks very similar, right? We are plotting the ACF using the .diff function, and it's showing it on the graph. As we can see, on the first lag is super, super significant. It's way out of the bounds that we have, which is that that blue like kind of area that a lot of the other lags are actually inside of. So it's way outside of that. So we know that having Q is equal to 1 in our model is going to be significant. And you can see Q is equal to 2. We could use that, but it's probably good to keep our model simple to start and see how well the forecast works, because you don't want to overcomplicate our model, right? And so here we're going to move forward with using Q is equal to 1. And so that is what we'll be moving forward with in terms of getting to an ARIMA model. So as you can see, we sort of built up between talking about seasonality, stationary, what an AR model is, and what a moving average model is, right? And so we're almost building to this point of using an ARIMA model. So what an ARIMA model is it's an autoregressive integrated moving average. So it actually combines an AR model with an MA model, and it has it be stationary, and that's what the integrated part means. So like we talked about, in an AR model, we had a value for P. So that was the number of lag terms we used, right? And we found that using the PACF test. In an MA model, we had a value for Q, which was the number of lag forecast error terms used that we decided to see what Q is going to equal to. And we saw that they're using the ACF test. And then we also had an order of different thing that we did before to try to make the time series data stationary, right? So if you remember, we did an order of 2 to make the time series data close to stationary. So in the ARIMA model, you have 3 parameters because it's using all 3 of these things and combining into one model. So you have 3 parameters: the number of lag terms to use, the order of differencing, which is D, and then Q is going to equal to, like in the MA model, the number of lag forecast error terms used. And so we can use this model to forecast our time series data very, very well. It's a very, very effective model. It's very simple, but it combines all of these things we've learned throughout today into one model. So we can actually project and see in a forecast of how many banana cells you're actually going to have. So as you can see here, we have a snapshot from the Jupyter Notebook, which is showing off an ARIMA model that is using a p-value of equal to 1. As you can see at the very top, it says the order is 1, 2, and 1, right? So what does that equal? What does that mean? Well, like we talked about, the ARIMA model has 3 parameters, right? So you have P and D and Q. So in this model, we have P is equal to 1, which means that we're going to be using, like we discussed before, one AR term from the AR model, which we found from the TACF test. We also are going to be using a D is equal to 2, right? Like we see here, because D is going to be our order of differencing, and that's what we found out that gets our time series close to stationary, is having our D equal to 2. And then Q, which is going to be the number of lag forecast errors terms we use, which we found using the ACF test for the MA model for the moving average. And that's going to be equal to 1, because we also saw that that was definitely significant, and we're going to use that to start and predict our data here. And so as you can see, we fit the model and we save the results, and then we do some matplotlib, very simple, just to make this little plot here showing the actual data, which is in orange, which is the actual time series data that we had in the very beginning, and then the predicted data. So what is our ARIMA model actually outputting, and what is it forecasting that the data is actually going to be equal to? And so as you can see, it's very, very close to what our actual data is. Of course, it's not exactly the same, but it's extremely, extremely close. And so we can be pretty confident in using this sort of model to forecast, okay, well, what is next week's data going to be? Because now we have an example. It's showing, well, it's able to map pretty well of what the actual data is based on these terms that we looked at, right? And so as we can see, the forecast is pretty accurate in comparison to the actual data. And this is using an ARIMA model of P is equal to 1, D is equal to 2, and Q is equal to 1. So yeah, that's basically the ARIMA model. It combines all the things we've talked about today, all these terms in time series forecasting, into one model where we can actually use it, and we can simply import it right into Python like we did in the very beginning. And now we can actually use it on our time series data to forecast what it's going to be and map it very, very well. And so now you guys kind of understand what the different aspects of an ARIMA model are, as well as overall, these are very common terms that are talked about in time series regarding being stationary, seasonality, what autocorrelation is, doing different tests to see how many lags to use. Those are all very, very common things that are discussed when you're working with time series. So it's really important to gather that understanding before you jump into even using a model, even as simple as ARIMA. A lot of the stuff we discussed in this workshop can be delved way deeper into. There's a lot, this is a very high level idea, so you kind of understand what is going on in terms of the different models and the different terms in time series forecasting and analysis. But I hope you guys got an understanding of how everything works. And if you're interested in this sort of thing, by all means, I recommend diving deep into a data set and trying out forecasting something, trying to pick different values of your lags. Like in this example, for instance, we could have picked a different value for how many autoregressive terms we want to use, right? We only chose to use 1, but maybe you use 2, maybe you use 5, maybe you use 6. I mean, the more terms you use, the more complicated and slower your model can get, but maybe the more accurate it can be. So it's all just about experimenting. There's also a lot of tests you can do to see what is statistically significant, when a time series is stationary. There's different things you can go more into. But yeah, it's a really, really good way to forecast any sort of time series data you have is using an ARIMA model. A question in the chat. Since we have this ARIMA model, would we use the other ones to make up this one? So actually, it's not quite how it works, right? So the other ones, so an AR model or an MA model, you can use those on their own. But an ARIMA model is just a way of combining a lot of different things in terms of stationary, like being integrated, having a moving average, and having an autoregressive term all inside of one model. And you don't actually have to like build it up. Like the code chunk that's on the screen right now, that's literally all you have to do to be able to load in an ARIMA model. Obviously, you have to do the differencing and you have to select how many lags you want to use, and you have to have a time series data set. But once you figure all that out, you don't actually have to build any sort of model. You can just import our ARIMA model, put in your data, and then select the different numbers for P, Q, and D. Is there any reason to have them individually? Any benefits? Why not always use ARIMA? Good question. So AR and moving averages, there are, like, let's say you have a moving average, but there's no autocorrelation between the previous data and like what you're trying to predict, right? That's what an autoregressive term is. You have an autoregressive term. So an ARIMA model is just a more accurate version of combining everything together. The different models have different ways of looking at and predicting a problem, but yeah, if you're able to get to a place where you can use an ARIMA model, then yes, it's definitely, you should use ARIMA if you can, yeah. And actually, there's an even further model you can use if you have a seasonality in your data. Like we even do here, we could make this even better by using a SARIMA model, which is a seasonal autoregressive integrated moving average model, which we didn't get to today, but that's also a model you could use. Does the model predict given only one starting data point? Sorry, I don't quite understand the question. Does the model predict given only one starting data point? Sorry, R. I might need you to just clarify the question a little bit. By the way, yeah, this is the slide for a question. Since the model predicts using historical data, yeah, so the model predicts using historical data. That's how a time series model works, right? It can forecast into the future. Do you need to input a starting data point to get the model going? Yes, you do, yeah, because that's how it's able to actually work, right? You can only have an ARIMA model if you were to have some historical data. You can forecast into the future with no real data. So let's say I want to know how many banana cells are going to be in 3 weeks from now. You can absolutely do that. And I didn't show that off in the code here, but you can definitely do that. You'll just see basically this trend of an orange line increasing and going, you know, further and further onwards, likely going to be mapping what the blue line, mapping what the actual data is going to be in the future. That's what you would use it for in terms of predicting something, right? Is the more historical data the better? Is there a point where it doesn't matter or it doesn't make a difference? Good question. So with machine learning, this isn't machine learning, right? This is time series forecasting. Machine learning definitely really benefits from having more data, especially with when it's making those correlations for you, right? If it's making correlations for you, then it doesn't want to make correlations between incorrect data points that aren't actually correlated. So the more data you have in an ML model is absolutely better. But in terms of time series forecasting, it's definitely better to have more historical data. By all means, it's not as big of a deal versus like using any like ML algorithms. But definitely, yeah, the more data you have, the better it's going to be. Absolutely. Yeah. That sparks another question then. When would I choose an ML model than a time series forecasting model? Can both do the same? Good question. So in terms of time series forecasting, it's useful for when you have time series data, right? ML models can have, you can have unstructured data, you can have structured data, you can have data where you have, like we talked about, like what is time series data, right? It's, you have one value for every, one value on the y-axis for every value on the x-axis, right? So your data point. So in terms of like that's time series model. So that's where you use a time series forecasting model. And you can't use a time series forecasting model if you don't have that relationship with the data and dates. If there's not some sort of data over time and only having one value on the y-axis. You can use ML algorithms to work with time series data. It's much more of a restriction between time series forecasting data, between ML data, but also ML models. There's a ton of ML models. There's ones that for unstructured or structured data. That's a whole other can of worms. So there definitely are, yeah, benefits to using either of them. Okay. So thank you guys for listening. If there's any other questions, please put them in the chat. I really appreciate you guys for coming out and listening. And you know, I appreciate you guys trying to learn more about data science. I really think if you guys stuck around this long, you should, if you're not already, join the Data Science Club. It's a really awesome way to get experience with data science, meet other people in the field, and yeah, maybe also apply to being an exec at some point. It's a great time. So also, please can you guys leave some feedback at this link on the screen here. I do appreciate any feedback I can get, whether it's positive, negative, just let me know. Just so, because it helps me with workshops in the future and as well as Data Science Club. So if you guys could go to this link and just, yeah, drop what you thought about the workshop. I'd appreciate that a lot. What kind of work is going on the data science team right now? Okay, interesting question. So I'm actually an education executive. So right now what I do is I'm involved with like this. So I'll be having my own workshop that I'll be presenting to you guys to be able to teach something to people who are part of the Data Science Club, as well as there's reading groups that you can actually join and be a part of, which are discussing different papers in machine learning or in natural language processing or whatever really we're interested in that week for reading groups. So that's kind of what the education group is right now. And data science team as a whole, I mean, we're doing lots of things. You know, we're doing different events. We have a really cool program actually called the Project Program. I'm not sure if it started already. I think it has, but we will be having one as well next term. I think, Alvin, right?
Stay tuned early next term, maybe January, for Project Program.
Yeah, I really recommend you guys, if you guys aren't interested in getting experience with data science, try out the Project Program. I have done it before. It's a great experience. You're able to make a project with some other people and then present it at the end. It's really fun. It's a good way to get some experience, get a project on the resume or on your GitHub or whatever, or just learn. It's a really good way to learn. I find with data science especially, the best way to learn is just by experimenting and diving into data and trying things out. So I recommend all you guys to take what you learn from this and try out some time series forecasting yourself. But yeah, Project Program is a great way to get involved, and that's one of the things the data science team is doing right now. Will I share the slides? Alvin, go ahead.
Oh, sorry. Yeah, just for like the next month, there's data science across sectors, which is like the panel event that we host with like industry professionals and talking about how they got into the field. And yeah, it's a cool event, and there's like two socials and actually a lot more workshops to come. So look forward to that.
Yeah, that's for sure. Will I share the slides? Yeah, I can share the slides with you guys. Alvin, how can I do that in effective?
Yeah, if you can download it as a PDF and then upload it to the data science server to the workshop channel.
Yeah, sure. I'll put it in the Discord.
Yeah,
it'll be available there. Yeah, and no problem. Thank you for coming. Okay, so if that's everything, I think that wraps up the workshop. Thanks so much, guys, for coming. I really appreciate you guys leaving feedback and I don't know, just coming out and spending a little about 45 minutes with me and just learn about time series. Yeah, really appreciate it. Okay, and I will stop sharing my screen.